I'm going to start today by drawing an inverter layout. And we're going to look at it from a top view and a side view to begin our discussion on the different layers of the CMOS process. I have the benefit of being able to change the color of my writing at will. Fortunately, you guys potentially don't. So I'm going to colorize the heck out of this thing so that we can distinguish between the mask layers. I'm also going to upload the YouTube video and all that kind of good stuff after class so that you'll kind of be able to differentiate. So, excuse me, I'm going to start by attempting to define a transistor. All right, so what I have drawn thus far is an attempt at an NMOS transistor. Okay, so this region right here in green is what I'm going to call my N active region. This region right here in orange is what I'm going to call my P active region. My pink is going to be my polysilicon layer. And so this is one of the two transistors that make up our inverter. Now, on the right over here, I'm going to work to define my PMOS transistor. And so over here on the right-hand side, we have a PMOS transistor using effectively the same materials, at least at this point. But one extra thing that I'm going to need to do, I guess I'll first tie these gates to each other, like so. And then this next layer that I'm going to put in, I'm going to do it purple. Where this region is what I'm going to call N well. And then my last thing that I need to do is define my metal 1 regions. So this region that I've just drawn there in the middle is the output, or from your handout that I gave you guys on last Friday would be terminal B of the device, whereas the polysilicon gates tied together form terminal A. And then I also have a metal region over here, like so. Where this guy forms my supply voltage. Then I have a metal region over here. This guy is my connection to ground. So it's not the exact same transistor that I asked you guys to draw. It's oriented slightly differently. So the transistors have been rotated 90 degrees from the ones that I asked you guys to draw. Another very distinct difference here is that the PMOS transistor is of the exact same size as the NMOS transistor. Whereas I asked you to draw the PMOS transistor, I believe 3 times as large as the NMOS. And we'll talk about why we typically do that in a little bit. Okay, so this is a top view. When we design using electric VLSI, this is what we're doing, okay? But a more helpful look at this guy might be a side view. So let's transpose this guy and see how this inverter is implemented on kind of a layer by layer basis from the top down. All right. So I'm going to start with a substrate. And for the sake of argument, I'm going to say that my substrate encapsulates this whole thing. And I'm going to draw this not in the order in which the processing steps would happen, but in the order which will allow me to turn the figure by 90 degrees the most easily. And then we're going to talk about things in the order that the processes will happen. So I'm going to define my P active regions first. So there's one. There's another. There's another. Inactive regions. Like so. Let me do my poly next. And this is going to be something that doesn't show up at all on our top-down view, our field oxide layer. So this gray that's scribbled through is field oxide. Will be a thin layer field oxide grown around that polysilicon like so. There's my N well. My black contacts, which I didn't label in the figure above. So I'll have to do that momentarily. So these black boxes, contacts, and then finally my metal layer. So we have metal 1 in light blue, poly in pink, orange is still reactive, green is still inactive, purple still and well. This black guy right here is still a contact. This gray is our field oxide. Anything seem to be not labeled between the two of them. So these are the two different views of our inverter circuit. So my question to you guys, ballpark, how many masks do you think are involved here? Or first, I guess, do you know what a mask is? So you guys have learned a little bit about photolithography at this point then, right? Yeah. So a mask is nothing more than what either blocks light or lets light pass through to form a particular layer in the photolithography and then CMOS process. Okay. So a CMOS circuit is built from the bottom up. The first thing that we have access to is a raw wafer that forms our substrate, and then we have to do some sort of processing to put in our wells, and then some more processing to put in our polysilicon gates, and then some more processing to establish our active regions, and then some more processing to establish our contacts, and then finally some processing to put our metal layers. And then there's actually some steps beyond that, like the overglass protection and all that kind of stuff, so your metal layers don't peel off, kind of holds everything down, all that stuff. We are going to talk about this in this class, literally starting from the bottom at the substrate and working our way all the way to the top layers that we're going to have access to. I'm going to supplement these talks with different applications of the layers that we're going to see as well. For instance, anybody know what the N-well region here is doing for this PMOS transistor? Anybody have any idea why it absolutely has to be there? So what if I told you that our substrate was P-type semiconductor material? Does that change your answer in any way, shape, or form as to why the N-well needs to be there? Any thoughts whatsoever? So if we didn't have an N-well, we would have a P active region here and a P active region here, and then P-type material down here as well. So would we form a transistor? No, because we would have P material, P material, P material, all that kind of stuff. So this N-well is effectively acting as a localized substrate for these PMOS transistors, or this particular PMOS transistor. But in a general sense, the N-well is a localized substrate. Any questions about any of this jibber jabber before we move on and get a little bit more formal about anything? All right, so let's talk about substrate first, because this is what we start with for design. What are CMOS integrated circuits built on? Anybody? No. Pardon? Wafers, yeah. So our substrate is just going to be, so we can say that CMOS circuits are built or fabricated on typically silicon wafers. So I say typically because a bulk CMOS process, like what your large chip manufacturers, Intel, AMD, all those guys use, is a standard silicon wafer. Usually P-type doped. So that means that the doping concentration when they are growing the crystal ingot is somewhere between 10 to the 13 dopants per cubic centimeter to 10 to the 16 dopants per cubic centimeter. They grow this big ingot by the Chozralski method, which I think you guys probably learned about in 334 at the beginning when you were learning about semiconductors in general and how they're grown and all that kind of good stuff. If not, there's lots of awesome videos on crystal growth on YouTube and all that kind of good stuff. So in that method, they put a very small seed crystal into what they call a melt of just amorphous heated up silicon. And that small bit of crystalline structure begins to propagate out, and then they pull the ingot up from that melt, forming a large tubular, or I should say cylindrical lump of single crystalline silicon. And during that process, they can add dopants in there and all that kind of good stuff. Now, we'll talk about the dopants and all that kind of stuff in a minute. That's how the overwhelming majority of CMOS circuits are built. It's on a simple silicon wafer, but certain applications require different mediums, okay? So when I was doing an internship with the Air Force Research Labs up at Wright Pat in Ohio, they were doing everything on gallium nitride wafers. Gallium nitride is a binary semiconductor because it's formed from two compounds, one in group 3 and one in group 5, and it has vastly different electrical properties and thermal properties than silicon. So they were using it because they were developing sensors and stuff like that to see what's happening in the engine of their jets. So they needed a very, very high degree of temperature stability. Whereas a chunk of silicon, the number of carriers can vary vastly over 100 degrees Celsius range. In gallium nitride, things are much more stable. And so they can kind of look at the different phases of when the engine is on and all that kind of good stuff to see how things are performing. A relatively modern substrate is what's called silicon on insulator wafers, where you have single crystal silicon and then a thin layer of silicon dioxide, and then a very thin layer of epitaxially grown silicon on top of that. So it's kind of like a sandwich structure. It's like an ice cream sandwich, except the base is much, much thicker than the other layers. The circuits that you build on a silicon on insulator wafer have a high degree of parasitic shielding due to the presence of that insulator layer. So we're going to be talking about parasitics in this class a lot. They are going to determine a lot of different things about what we can do. Well, if you have this insulator layer, separating your substrate from a big conducting plane, which is all that bottommost layer of silicon is, you get rid of a lot of the parasitic effects, which is typically good, but you're limited in what you can do. And then there's also now, instead of having a silicon dioxide, which is effectively an amorphous glass insulator layer, they have insulator layers made of sapphire. And those are for really, really high-end, high-frequency components. So like on the order of 350 gigahertz and higher, electronics require a sapphire insulator in order to block all those parasitic effects and make anything useful. All right, so CMOS circuits are fabricated on a silicon wafer. And then these wafers are doped with donor atoms, such as phosphorus or arsenic, to make Ptype wafers, or acceptor atoms such as boron or gallium to make P-type wafers. Typical doping concentrations, as I mentioned before, range from 10 to the 13 per cubic centimeter to 10 to the 16 per cubic centimeter. Do any of you guys remember from your 334 class or anything like that? This might have also been covered in 437 or MSc 501, depending on whether you're an undergrad or a grad student, what the atomic density of silicon is. So how many atoms per cubic centimeter? So the atomic density of silicon is 5 times 10 to the 22, roughly, atoms per cubic centimeter, okay? So if we were to dope a crystal with a dopant concentration of 10 to the 16 impurities per cubic centimeter, we would be replacing 10 to the 16 atoms of silicon per cubic centimeter, okay? That seems like a whole heck of a lot, right? Because it's almost, well, I say it's let's see, so 10 to the 16 would be 10 million billion, right? 10 million billion atoms that we're replacing, which seems like it's going to make the silicon behave not like silicon very much. But in truth, 10 to the 16 atoms per cubic centimeter of impurities makes our silicon 99.99998% pure. So even though we're putting in 10 million billion impurities, it still behaves as if it's practically pure silicon, right? That's incredibly important, because if we changed the behavior of our substrate too much, we're not going to get our expected behavior for our device at all, okay? In standard CMOS processes, P-type 100 wafers are traditionally used. Do you guys know anything about Miller indices at all yet? Okay. So, all right, great. Learned about Miller indices this morning. Okay, so I don't have to go into that too much. Effectively, all that's going to mean, all the, well, I'll draw it just for the hell of it. So let's say that we have a crystal and it is simple cubic because I'm lazy. Any of the faces of this crystal would be a 100 plane, right? So any of these 6 faces of this simple cubic crystal would be a 100 plane. Now, because of the way that silicon is structured, it has a diamond configuration, or zinc blend is what you would call it if it were 2 different atoms. But effectively, it's actually 2 face-centered cubics superimposed kind of inside of each other. And so what that means is that silicon is very, very anisotropic. So in particular directions, it has some properties, and in other directions, it has vastly different properties. So for a 100 plane at the surface, that's got the least atomic density per unit area available. Whereas the 111 plane, so the 111 plane, I'll draw in red here because this is the other one that gets used a lot. Has the highest atomic density, which means when we do chemical processes on a silicon wafer with a 100 oriented face, we are going to see that we get angled etch troughs. And you guys are going to learn all about that kind of good stuff in your 437/MSc 501 class. Okay, it's kind of beyond the scope of what we're doing here, but I just want to give you as much kind of starting off information as possible. All right, so if we wanted to form a NPN transistor, things are pretty trivial, right? Because we have a P-type substrate that we would be dealing with, so we would just have to figure out how to make N regions. I'm going to talk about in a couple of days, but overall things are pretty simple, okay? If we wanted to make a PMOS transistor, though, we run into issues because we will not have a PNP region to work with to make our transistor. So that's where we're going to go next, is with our well layer. But before we do that, I want to talk specifically about how we fabricate our well layer, okay? So if we start with a substrate, and I'll draw this one a little bit smaller than previously. So we're starting with our P-type substrate. The first thing that we would do, step 1, would be to cover the entire surface of the wafer with a protective oxide, which we'd form using silicon dioxide, which effectively just means we need to put the wafer in an oven in an oxygen-rich environment and kind of let things happen. The longer we leave it in there, and the temperature at which we have the oven set at determines the rate of growth of the oxide layer, which is something else you guys are going to talk way too much about in your MSc 501/437 class. But again, so that's what's going on there. All right. So if we want to implant a well into this, what we're going to have to do is decide where we want to put that specific well. And we do that using photolithographic processes, which it sounds like you guys are already learning about, right? So we would spin a layer of photoresist. I'm trying to think of a color that I haven't used yet. We'll do this yellow. Actually, don't think that'll be wildly too difficult to see. Let's do brown. I think that's brown. Spin a layer of photoresist. And then we would use a mask to define effectively which regions of photoresist we want to keep and which regions of photoresist we want to wash away using our development, okay? So for the sake of argument here, let's say that we've done a simple photolithographic process like you guys are familiar with. And we have a hole cut out of our photoresist from exposing the photoresist to the ultraviolet light and then rinsing it through a developer and all that kind of good stuff to get rid of all of the unisomerized chains, okay? We would then we'd use our N-well mask to pattern this guy. And then we would have to etch with hydrofluoric acid. So let's see here. Step one, throw the oxide layer. Step two, was apply photoresist. Step three was pattern photoresist. Step four will be chemical etch with HF. Any of you guys know anything about hydrofluoric acid? So those of you that work for Chester know about it. It is nasty stuff. How many of you guys watch Breaking Bad? Season 1, episode 2 of Breaking Bad. Jesse Pinkman tries to dissolve a body in his bathtub by using 2 gallons of hydrofluoric acid. There are some parts of that scene that are very accurate, and then there are other parts of that scene that are very inaccurate. So let's talk about the inaccurate ones first. HF is not going to dissolve a body because that's not what it does to organic tissue. What hydrofluoric acid does to organic tissue is it seeps in through your skin and it leaches the calcium out of your bones, forming calcium crystals in your bloodstream, which will slowly give you a heart attack. It only takes about 1% skin exposure to kill you in about half an hour. It is ludicrously dangerous stuff. So what you typically do to counteract it is you're wildly careful and wear as much PPE as you can stomach. And then you keep a tube of what's called calcium gluconate gel on you or nearby you at all times. Because what that is it's a basic solution, so it'll neutralize the acidity of the HF. And it also provides a lot of local calcium for the HF to interact with so that it doesn't leach into your bones and kill you, okay? HF is wildly, wildly dangerous stuff. I'm assuming that since you're taking this class, you might at some point have to work in a clean room. So let's start your absolute fear of dealing with HF here, because you should be afraid of it, to be entirely honest. The parts that Breaking Bad got right are its ability to eat through glass and metal and pretty much inorganic material that isn't polyethylene based, right? So I don't know how like this was legal, but back in the day, if you wanted to do like a frosted glass window, what people did, tradesmen did, was take the pane of glass and effectively fill a squirt bottle full of diluted HF and then spray it on the glass, wait a couple of minutes, and then rinse it off because it would eat through portions of the glass, giving you that nice frosted look. How the people that did that didn't kill themselves on accident constantly is beyond me. HF scares the ever-living bejesus out of me, okay? So what it's used for in this process is to get rid of all of that silicon dioxide, right? It actually won't eat through that photoresistor. If it does, it's going to be very, very slowly. It's going to eat through the oxide much more aggressively. And so it's going to wind up effectively cutting a hole exactly where the photoresist told us the hole should be, okay? Because the HF, again, is going to eat through that silicon dioxide much, much more aggressively than it's going to eat through photoresist. You can even use the cheap stuff. You don't even have to use epoxy-based photoresist to withstand HF. But for ceramics, glasses, all that kind of good stuff goes through it real quick. Metals, it's ludicrous how fast it'll eat it. All right. So the next thing that would be done here would be ion implantation. It used to be that you could do diffusion. So you could effectively sputter some, in this case, it would be acceptor atoms over the entire surface of the wafer or whatever, and then effectively heat things up, and the concentration gradient would drive the donor, the acceptor ions into the silicon. But nowadays, to make things faster and as small as we want, we typically do ion implantation, where we have a beam of ions and we shoot them into the substrate itself. And it just breaks silicon bonds, knocks things out of the way, and effectively interstitially replaces silicon with our ion of choice. You can actually do that to image things as well. So that ion implantation is going to result in the formation of our N well. So now we're going to talk about our N well a lot. All right. So as I mentioned earlier, N well region acts as a local substrate for CMOS transistors. It is formed via ion implantation, usually. So this process where we're firing ions into the substrate is what we're going to refer to as a counter or compensation doping process. Okay. So let me explain what I mean by that. And again, you guys might have talked about this to some extent in your 334 class. So we're starting, let's say, with a region of P-type crystal, which means that there are, just for the sake of argument, let's say 10 to the 13 acceptor atoms per cubic centimeter, okay? And our ultimate goal is to make this region N-type, okay? Which means we have to completely counteract the effects of all of the acceptor atoms to bring it back to an intrinsic state. It won't actually be intrinsic because it will now have 2 times 10 to the 13 impurities in it, right? That would bring it back to behaving like an intrinsic silicon crystal, except that it would have slightly worse characteristics because of all of the impurities in it. And then we have to dope beyond that in order to make it actually be N-type, right? So that's what counter or compensation doping means, right? We have to exceed the original doping concentration in order to flip that region of the crystal from a P-type material to an N-type material that can be used to form that localized substrate. All right. This process is a degradative process, okay? It actually makes that region of the crystal behave worse. And it's because we have a lot of electron hole pair recombination, right? So we have a region that has a lot of holes in it because we put acceptor atoms in there. And then we're firing a whole bunch of donor atoms in there. And so we have a region that has a lot of excess holes and a region that has a lot of excess electrons. And those electrons and holes are going to recombine. And what are they going to leave behind? Anybody got any idea? So the boron atom, let's say that we're going to use boron. When it has its excess holes, is it electrically neutral or is it an ion? Is electrically neutral, right? Crystalline boron is electrically neutral. Even though it has places for electrons to go, it doesn't actually have extra, or it doesn't have less electrons, right? So a hole just means there's an extra place for an electron to pop in and form a bond and then jump right out, right? Similarly, crystalline arsenic or crystalline phosphorus, even though it has extra electrons for mobility's purpose, it's electrically neutral as well. But when you have all those electrons and holes, those free charge carriers and places for free charge carriers to go and form a solid bond, what's left behind is a whole bunch of ions with no free charge carriers to speak of, right? That's really bad because it prevents a lot of localized places for more scattering events to occur, which means that we're going to have lots of places for electrons and stuff like that to bounce off of, which is why the carrier mobility is going to be very, very low in those regions, which is actually why we wind up having such, that's why we have to make our PMOS transistors 3 times as large, because our whole mobility is going to be 3 times as low. Because if you think about what we're doing here right now, we're just forming the well, right? So we're doing a compensation doping process. We have our P-type material, we flipped it to N-type. Later on, we're going to have to set up a P-active material on top of that, which means we're going to have to compensation dope that N well again. So we're degrading it even further to change parts of that N well back to P-type. We are messing stuff up a whole heck of a lot in that process. The only way you can never get around it. Okay, let me start there. You can never not do that. But your best bet to cause the most or the least amount of degradation is to start with the lightest doping concentration that you can, because it's more easy to overcome. And so you're leaving behind less bound ions to mess things up. Does that make sense? Okay. All right. So the N well is fairly, as a localized substrate, is fairly easy to understand, but it can be used for more than forming that localized substrate. Okay. So the N well can also be used to form resistors. And we're going to spend some time on this because you're probably less aware of this capability. So in addition to being used for CMOS bodies, N wells often used to create resistors. In CMOS integrated circuits. Okay, so there are several different ways to go about creating a resistor. I say several, there's like 3 actually. But this is one that is very, very common because you don't have to do any special processing whatsoever. It's always available to you, okay? So going back to an equation that you guys first saw in Engineering 121, still coming back, you may recall that a rectangular section of material has a resistance of R. The resistance is equal to rho, the electrical resistivity of the material, multiplied by the length of the material, divided by the cross-sectional area of the material. And we can rewrite that expression as rho E multiplied by L divided by T, the material's thickness, multiplied by W, the material's length. So I'm going to draw a little picture here that will hopefully help illustrate what I'm talking about. All right, so here is our length. Here is our width. Here's our thickness. And so this face is what I'm calling to be the cross-sectional area of the material. Okay. In a semiconductor process, the depth or the thickness of the N well region is identical for all N wells, right? Because you would create all of the N wells in a single processing step, okay? So you would do your photolithography process to pattern where you want all of the N wells for the entire wafer to be all at one time. You do the HF etching to get rid of that silicon dioxide, and then you would expose the entire surface of the wafer all at once. So they are all going to have the exact same thickness, which means the thickness of our And well, resistor is no longer important because it's common to literally everything, right? So we could say that for an N-well resistor, we are going to have what's called R square. Okay, so that's supposed to be a little square there, multiplied by the length of the resistor divided by the width of the resistor, where R square is what's known as our sheet resistance. And it has units of ohms per square. This is a fairly interesting unit because, well, interesting to me, hopefully interesting to you, but you probably haven't talked a whole heck of a lot about sheet resistance at this point and what a unit of resistance per square means. Anybody have any idea? So let's say that we were looking at a top-down view, okay? I'm gonna write down here, I'll do it in blue. So this is kind of a little something extra. So let's say that we had a chunk of material, and it is 100 microns wide by 100 microns in length. Let's say, for the sake of argument, we have an R square value of 100 ohms per square. The resistance of this chunk of material, or this surface of material really, would be 100 ohms because it's a square. If I instead had a 60 micron by 60 micron surface, what would the sheet resistance be? Still be 100 because it's a square. So it doesn't matter what the dimensions of the square are. If we have a square shaped section of material, its sheet resistance is 100 ohms per square, okay? So this might seem weird, but we can think about it in a different way, right? So I'm going to subdivide this guy into 4 smaller squares, right? So let's say that we were trying to pass current down this way and have it come out this way. What does it see? Well, it sees this terminal effectively. I was not trying to erase that. I guess I'll have to do it in a different color. So it sees this terminal. It sees a square in parallel with another square, right? So we would have, or excuse me, so on the left-hand path, if you want to think of it that way, we have 100 ohms resistance per square in series with 100 ohms of resistance per square, forming 200 ohms of resistance in parallel with another 200 ohms of resistance, giving us 100 ohms overall. And you can subdivide that as many times down as you want, or blow it up as many times as you want, and it's still going to behave in that exact same way. So a square does not matter what its physical dimensions are. If it is square, you treat it as having a resistance of R squared, okay? So if we wanted a 250 ohm resistor, what would we have to do? So let's say it won't be square, that's for sure. That's actually a critically important thought here, right? So I'm going to start with one square. That's going to be effectively 100 ohms. And then I have another square, 100 ohms. And so when I put these two guys in series, I get 200 ohms. So that part's easy. How do I get 50? Yeah, half a square. Because it's going to be effectively 100 in parallel with 100 when we subdivide it, right? So we can make any resistance value we want by just defining the length of our resistor with a fixed width. Right, so if we want, I don't want to do the math in my head for like a 10 kilo ohm resistor, a crap ton of squares in series, right? But it always has to be longer than it is wide, because if we widen it, we're actually reducing the number of squares, which winds up reducing the resistance of it, okay? So we got to pay attention to all that kind of good stuff. So if we wanted to make a large resistor, ostensibly, we would need to take up a lot of real estate on our wafer, right? Not necessarily a lot of surface area per se, but if we wanted a large value resistor, it would be very, very long at a minimum. So what we could potentially do to mitigate things like that is create a serpentine resistor, okay? What do I have? This class ends at 1:45, right? Yeah. Okay. All right, so for a serpentine resistor, and I'll try to draw this as best I can if I can get back to my sheet here. No, stop scrolling. So we might have something go away. Like this. Okay. Where we can see that it's really just a bunch of squares connected in series. We do have a very small problem. We'll talk about it momentarily, right? So to me, this looks like, let's say 5, 6. Actually, that's the dumbest possible way to do it. 5, 10, 15, 20, 25, 30, 31, 32, 33, 34, 35 squares. So this would be ostensibly a 3.5 kilo ohm resistor if we had 100 ohms per square, right? Except that it's going to be smaller than that. The reason why it's going to be smaller than that is those corners, okay? So in a straight line for a DC voltage signal, we're going to have a nice and easy, well-defined current distribution throughout the whole thing. It's going to spread evenly. But when the current tries to round those corners, more current is effectively going to be bunched up over here, and almost no current is going to happen on the outside edge when that electricity flows through. So the sheet resistance of a corner is going to be approximately 0.6 sheet resistance of a linear square, I guess is the best way for me to explain it, okay? So with that in mind, how could, let's say that R square here is 500 ohms. What should our overall resistance of this guy be? So how many, I would approach this by figuring out how many not corners I have, and then figuring out how many corners I have, and then doing a little bit of algebra, right? So I'm going to put a blue dot in my not corners. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 25 not corners. And then 1, 2, 3, 4, 5, 6, 8, 9, 10 corners. $25 times 500 plus 6 times 500. It's 31 times 500, 17,000, no, 15,500.
Why can't you just reduce it?
Okay. So that's a good question. So why can't we curve the edges, right? That's effectively what you're asking. So you could pattern a curve ostensibly, like in the photoresist and then in the ion implantation phase and all that kind of good stuff as well. So what my original thought was, I had to deal with the planarity of everything that's created in a CMOS process, how it needs to be, right? So like, what I mean by that is you'll practically never see CMOS inductors because to make a coil requires a three-dimensional structure, which effectively isn't available, or it certainly isn't available in a standard CMOS process. But to curve a resistor actually doesn't require you to change the three-dimensional aspect of it at all. So the short answer is I don't know, but it's just not done in practice. Like when we look at the tools that we have, everything is defined in terms of a rectangular grid. And so if you don't have access to not using a rectangular grid, I don't know how you could actually get a curve. Like you could fake it by doing kind of a stair step type configuration, but then you get into the issue of, well, okay, so how many how many squares do I break that stair step configuration into? And how do I count them all versus the simple approximation of, I'm gonna say the corner is 60% because that's what my experience tells me. Saying the corner is 60% is probably a little bit easier. So yeah, I mean, legitimately, I don't have a really good explanation for why it's not done in practice, other than it makes the math way harder than just saying, this is about 60%. So, yeah. Now, if, this will be the last thing we're gonna talk about today, because we only have a couple of minutes here. So, the corner being roughly 60% of the sheet resistance, that's fairly uniform. That being said, process variations and all that kind of stuff can mess with the value of a resistor defined in this way pretty significant, right? Because it depends on all of your squares being roughly the same size, everything being laid out to very specific lengths and widths and all that kind of good stuff. In analog systems, much more so than digital systems, where the actual value of the resistor itself matters, we do serpentine resistors in a very different way. So a serpentine resistor, so this would be more of a digital serpentine resistor because the discrete value of the resistor isn't nearly as important. But for an analog system, which is what we are going to be designing, we would instead design simple fingers like this, and then connect them using wires, which is effectively just the metal layer, right? So we would have to put a contact in, contact, 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 contact like so, and then connect them using strips of wire, and we'll talk about that a lot more once we get into actually really discussing what the metal layers are and how they behave and all that kind of good stuff, okay? And the reason why we would break them down into individual fingers and stuff like that is what's called a common centroid topology. And we'll talk about that. I mentioned it to my 336 class, I think, as a way to minimize process variations when we were talking about something having to do with analog electronics last spring, although what exactly we were talking about has escaped me at this point. But effectively, there are ways that we can lay things out where if we have a well-defined understanding of how our misalignments are going to occur, then we can develop schemes to counteract those misalignments as they propagate away from the center of the chip, right? The center of the chip, or the center of the wafer, is where everything is going to be the most aligned. And the closer we get to the edges, the more misalignment we're going to see, which means the physical dimensions of everything that we've designed are going to be skewed, typically in multiple directions. And so to accommodate that skewing, we have to think about, all right, so if we know the further away we get is going to be more skewed, well, we'll probably spend an entire day talking about the common centroid methodology for laying things out. But there are tricks in place to get around that. And one of those tricks is not using the corners at all, but effectively connecting through the wires. All right, I think that's enough out of me for today. So on Wednesday, we're going to keep talking about our N wells. We're going to talk about some of the rules for why they have to be spaced certain ways and all that kind of good stuff to avoid creating parasitic transistors, which would be very bad. And then talk about accidental parasitic diodes, accidental parasitic capacitances, and then look at an N-well resistor as an RC transmission line, because that's actually what it forms. So, all right, see you guys on Wednesday.